Okay, right. So welcome to the lecture. We are still discussing applications of Grabner basis for certain computations in polynomial rings. So we are now looking at operations on ideals. So maybe I just repeat the heading of this subsection, operations on ideals. Okay. So maybe before I repeat, last time we had some geometric interpretations of what we are doing. And this interpretation always requires that the base field is algebraically closed. Okay, so actually you don't need to understand these applications in very much detail, but it is very nice to have it. Okay, on the other hand, I mean, these algorithms that I'm going to explain, they work for any field. So I think I really want to make clear this distinction. Geometric interpretation requires algebraically closed field, but like the algebraic method works in full generality. So I want to clarify this issue a little bit because last time it was not very clear. So, okay, we are given polynomials f1 up to fr over in the polynomial ring in n variables x1 up to xn over the field k. K is any field. Then we look at the following ideal. Let's call it J. So what I have R additional variables, y1 up to yr. And then I look at these polynomials, y1 minus f1, etc. Y4 minus fr. So, and this is to be seen as an ideal in this larger polynomial ring. I have the x variables and I have the y variables. Okay, look at this ideal. So the interpretation, so I keep in parentheses the interpretation, but it will not be required to know this. But of course, it's good to know it. Interpretation was this. This J is the vanishing ideal of the graph of the corresponding polynomial map. So J is vanishing ideal of graph of the map. Let's go F from K to the N to K to the R. And this F just has the components F1 up to FR. Okay. So this is, so we discussed this last time, I think in quite some detail, but in order to be very clear here, it's good to assume that the field is algebraically closed, etc. Okay, this is just side information. Okay. Right. So now, so what can we do with this ideal? So let's assume I have any polynomial in the x and y variables. So any, let's call this g. I have a polynomial g in x and y. Maybe I just abbreviate to write it this way. Can be written as, so I claim I can any g write in the following form. It's a linear combination of the yi minus fi plus some remainder r. And this remainder is a polynomial only depending on the x variables. And it's unique. Okay, so how can we show that? I know, any idea how one could see it? So maybe for clarification, I should say ui is a polynomial in x and y. Okay,
So we need to consider a reduction with a Grobner basis, which is given by these
Very good.
polynomials.
Very good. Very good. Right. So actually, I mean, before you were in my lecture, I think, but you knew how to deal with polynomials in one variables. Maybe you learned it in high school. Okay, just if you have one variable, then you can do, okay, you can do a division with remainder for univariate polynomials. That's certainly one idea. I mean, if you see this and you don't know Gröbner basis, you would say, okay, I take G, I try to make a division by y1 minus f1. Okay, but then it's maybe not completely clear what to do. You should view it as a univariate polynomial, and then you can succeed. But now we have this Gröbner basis theory, and as Lev said, it's completely correct. We can apply this theory, and then it becomes very clear. So, okay. So I will give the argument in a second, but let me complete my claim. I also claim this polynomial G is in the ideal J if and only if the remainder R equals 0. Okay, and the reason is this. So here we can see the Gröbner bases are also not just useful for computational purposes, but also for mathematical reasoning. So namely, y1 minus f1, this list of polynomials is a Gröbner basis. Okay, now, of course, it depends on which term order. You have to choose a term order where the y's are the large variables. So let's say with respect to the lexicographic order, such that the y's are ordered this way. First come the y's and then comes the x's. Okay, we know that because we can just apply the Buchberger criterion. Then the leading terms are the y's and they are pairwise coprime. So it's a Gröbner basis. Okay, and then we know division with remainder by a Gröbner basis. We can do it. There is no problem. The final remainder, which is the normal form of G, modulo the ideal, is uniquely determined. This is exactly the R. Okay, this is exactly the R. So I use division by this Gröbner basis. Okay, R is the unique. What do I write? Normal form, unique normal form of G modulo the ideal. Okay, and then everything is explained. Okay, good. So what does it help us? I thought, okay, actually I want. So what I want to discuss here, okay, I forgot to say, the discussion, okay, there are several applications. So the application here I want to discuss is on subalgebras. I forgot to say subalgebras. In the last session, I already started with this, but now I want to continue. So subalgebras.
Could you please maybe very shortly recall the concept of subalgebra, because I doubt that we really had it in detail in algebra 1.
Okay, good. Right. So I just think what is the best moment to do it.
But maybe
okay,
if others,
I will recall it. Okay, I will recall it, but give me a minute. I will do that. I will do it. But just to continue this reasoning, okay, if I have, okay, say I have a polynomial, my polynomial G before was in the x and y variables. Now assume it's only depending on the y variables. Okay, then we see, what do we see? Okay, we are here. We look at this. Okay. Right. So now I want to do the following trick. if I substitute my y variables by the f, I say yi should become fi. I make a substitution. Then these things become 0, and this whole contribution becomes 0. And so the g after the substitution becomes the r. Okay. So what I want to do is the g. Okay, the g depends on the y's, but I make a substitution. I hope it's clear what I mean by that. I just substitute the y variables by the f's. Okay, and what I get, it must be r. Because as I said, because this thing, it disappears after the decision distribution. Okay, so therefore, now we see something I introduced already last time at the towards the end, the ideal of polynomial relations, and I return to this. So I look at the set of all polynomials h in the y variables such that h, and I substitute the y's by the f's, and I get 0. So such an h is called a polynomial relation. It's a relation between the f's. Think of, for instance, if f would be a linear polynomial, then this would express a linear relation. Okay, good, that you know from linear algebra. But here we have also nonlinear relations. For instance, we could have f1 squared plus f2 equals 0 or something like that. So we want to understand this collection of all relations. And what we see, this is nothing but it's an intersection ideal. It's J intersected with the polynomial ring in the Y's. Okay, maybe. Okay. So this is, let me write, maybe in yellow. Ideal of polynomial relations. Of these f1 up to fr, and this is the elimination ideal. And we know already how we can compute elimination ideals using Gröbner basis. Okay, I hope, right, I hope this equality is clear. Namely, okay, let me just again go through it. Okay, maybe it's confusing before. Okay, I said the polynomial is called G, and now say it's H. The G is now H, okay? I use, because G was like for a general polynomial in X and Y variables, H is only the Y variables. But what we have, now this H, when I plug in the F's, is just this normal form, okay? And this is 0 if the normal form is 0. And this is exactly the case when my H is in J. So I assume I have an H polynomial only depending on the Y variables. Then I see this equals 0, which is the remainder, the normal form, if and only H is in J. So this is exactly that. Okay. Good. Well, any questions on that? So we didn't even use Gröbner basis in order to see that. The only Gröbner basis application was to understand, I mean, that we have this relation, but this was like an auxiliary applications. Okay. Good. Now, okay, subalgebras. Okay, what is the subalgebra? Now we consider, okay, let's say define, okay? So it will be clear, maybe a new page. Okay. The subalgebra of the polynomial ring generated by F1 up to Fr is the following. I mean, as always, I mean, I can define it abstractly. It will be the small, okay, right. You know what is a subring, of course, but maybe you don't know what is a subalgebra. Is that the problem? Okay, because that's important. What is an algebra over a field? Oh, then I should explain it. It's not clear.
I think it's clear now.
Okay, I'm just trying to find out whether everybody knows what is a subalgebra.
Maybe if anyone doesn't know.
Okay, so we also we are dealing in this we are dealing with commutative rings. Okay, so
the subalgebra itself, well, it's the subset of an algebra that is algebra. That's
right.
okay.
So I'm just trying to find out whether everybody knows what is an algebra.
But the problem was with subalgebra of symmetric polynomials. We have spoken about that, but I don't actually know what it is. I don't know if anyone knows.
Okay, but let me again say, if I have generally, okay, A is a commutative ring. Okay, and then subalgebra, a K algebra is this. K is a field. Then a K algebra is essentially that. I mean, with K algebra is a commutative ring. Okay, this is a commutative K algebra, I should say. Okay, we only do commutative here. So it's a commutative ring which contains as a subring the field. So then what you can do, the multiplication with these elements of K, you can view as scalar multiplication. And so the A also gets the structure of a K vector space. So it's simultaneously a ring and a K vector space. This is the K algebra. That's all. Okay. And I think it should be clear what is a subalgebra. It's a subring and should also contain the K. Or you can say it's a subring and the K subvector space. It's all equivalent. Okay, now let me write explicitly what is the subalgebra of the polynomial ring generated by the polynomial. I can write it explicitly instead of saying it's the smallest subalgebra containing F1 up to Fr. I can just write it in the following way. So I take any polynomial h in auxiliary variables y1 up to yr, and then I substitute the variables by the f's. So in other words, I mean, what I have here is just a polynomial expression in the f's. Anything you can obtain by arithmetic operations. Okay, you do addition, subtraction, multiplication, and you can use any field element. Okay, if you look at it, you see, you immediately check this is a subalgebra. Okay, it's immediate. It contains F1 up to Fr. And any subalgebra containing F1 up to Fr has to contain these expressions. So this is the subalgebra. And it's useful to have, okay, we can write it this way. I just write it this way, K, and then in the brackets. Okay, do I want to write it this way? I think I want to write it this way, yes. This is just a naming, okay, for this subalgebra. Okay, so this was a definition. Now the task. The task is, actually there are now two algorithmic problems, okay? Problems. Okay, for given Okay, when we talk about algorithms, there's always an input. So we are given polynomials f1 up to fr and the polynomial g in the x variables. For given there are two things. One is decide whether the g actually lies in this subalgebra. Okay. And if yes, compute an expression h. Okay. So maybe such that g is h substituted. You see? I mean, I hope you see the analogy. Okay. The analogy is this. If instead of algebras, we would just look vector, would look at vector spaces. Why not? Okay. We only allow addition and scalar multiplication. Then here, I would put a k-linear combination of the f polynomials. So what I would have in that case, here, this would just be the k-span of these polynomials. Okay. And then this algorithmic question is this. Given the f's and the g's, is g in the k-span of the f's? It's a typical linear algebra task where we know how to do it with Gauss elimination in this algorithm. Okay. But now we are like in the nonlinear generalization of that. It's clearly a harder problem. Okay. And the second is this. Okay. The f1 up to fr, they may have relation. I should have given an example. Okay. Okay. Yeah. They may have relations. They may not be independent. It's like if, again, going back to the vector space analogy, if the f1 up to fr are linear polynomials, there may be linear relations. Okay. And we maybe want to find out what is the set of all linear relations. The set of linear relations will be a vector space. Here, it's a more complicated. The relations are captured, I have, by this ideal of polynomial relations. Okay, a relation is such an H with this, and it's an ideal. And how do I describe an ideal? By giving generators. So I need to compute generators. But before we noticed, this is an elimination ideal, and we know how to do it, okay? Principle. But we know how to solve it. But let me write the task. Compute generators of ideal of polynomial relations. JF. Okay, so these are the problems. And we can solve them at least in principle. I always say in principle because in practice, I mean, you must understand, it's not like linear algebra. With linear algebra, you can solve, I mean, systems with, you know, thousands of equations, thousands of variables, 10,000, no problem if you do it right. Here, it's a bit more difficult. I mean, because these Grabner boxes get so huge. So there is a limit to what you actually can do. Okay, but it's still very nice to have this. So the solution, I shouldn't be so negative about Grabner basis. Okay, some people are much more positive. The problem is I work in complexity theory, and there you always think of the worst case. Okay, and that's why I'm a little bit, you know, if you think of worst case, it's not that great. Okay. So what is the solution? Solution. So I compute the Grabner basis, but I have to choose the right term order. Let G be the Grabner basis of my J. Okay, it's the J, that's the same J as always. I can write it for the sake of completeness. Okay, with respect to term order. It must be an elimination order. I can say of the nth. Okay, actually, I don't like this name, but I still say it, nth elimination type. So what is important here? I mean, if I, okay. I mean, this only makes sense. What does it make sense to say the nth elimination time? I have to order my variables. So the meaning is I order them this way. So I have first, I have a block of x variables, and then I have the block of y variables. And the monomial in the x variables, any monomial in the x variables, but actually there is some x, should be larger than any monomial in just the y variables. So this is the meaning. And to be concrete, we may assume we take, for instance, we take a lexicographic ordering, lex, with this thing. So as a word of warning, you should not be, I mean, you are likely to be confused here. I was also confused at some moment. Before, here, up here, when we did this reasoning, we also looked at this idea, and we took a Gröbner basis with respect to this lex order, okay, where the y's are big. And there we don't have to do any computation. The Gröbner basis is just there. That's the Gröbner basis, okay? But now we work with a different term order. Now we say we want to look at the term order where the x are big. And then it's a completely different story, okay? Then this transforms into something which is possibly complicated. Okay, so we do this. Good. And then, so one, now here is the solution to the task one. I compute the normal form with the division algorithm. Compute normal form. Let's call it H. H is the result of the division of G, small g, by the Gröbner basis. Okay, I compute that. Then I can say G, and this will require some proof. G is in this subalgebra if and only if what? Now, this H, let's see. Okay, the G, right. So my G is a polynomial in the x variables. Okay. The Gröbner basis will involve polynomials in x and y. I do this division. So in general, the result H will be a polynomial depending on x and y variables. But here the condition is it only depends on the y variables. So that's what I want to write. This is a polynomial in the y's. Okay. Okay. So I will, this is not immediately clear, I think. I will prove it. Moreover, if this is the case, if this the case, I have my relation, namely the H I computed is the relation. So we really have G equals H, substitute TTFs. So the task one is completely solved. Okay. Once you have the Gröbner basis, you have the Gröbner basis, and then you just do it. I mean, a division will remain. The division is not so hard, okay? And then you check this in the H. Is it a relation that you just have to check, is there an X variable there or not? If there is an X variable, it was not in the subalgebra. If there is no X variable, it is in the subalgebra, and the H gives the relation. Very beautiful. Okay, so I will prove this in a moment, but let me also state the solution to the second task. This, I think we already discussed. Okay, I pick a subset of my Gröbner basis G, namely the subset consisting of those polynomials which only depend on the y variables. This is a Gröbner basis of the ideal. of the ideal JF. And the reason is the JF is an elimination ideal. And we have this general procedure for computing elimination ideals. So I think 2 should be clear. Okay, so we needed the reasoning. We needed to understand the ideal of polynomial relation is an elimination ideal. And then we apply this previous method for computing elimination ideals. But I still need to prove part 1. So I think 2 is clear by what we have said. And I need to prove 1. Maybe I move this down. No, or is there any question? So anything?
I'm
Yeah.
sorry if you already explained this, but could you maybe recall why JF is an elimination ideal?
Okay, sure. This was here. This was, I frame it in this box.
Okay.
So
yeah.
this is because you see on the left-hand side polynomial relations, but on the right-hand side, this is, yeah, it's an elimination ideal. You have eliminated all the x variables. Okay, maybe
Yeah,
I
okay.
can. It's okay. Maybe I write it in yellow because people maybe will watch the video and look at the slides. X variables eliminated. Okay, you always need to, when you say elimination, you always need to know who is going to be eliminated. That's important. Okay. Actually, it's a bad word. It sounds like killing and so, but it was not my invention. Okay, so let's prove statement 1. Now let's do this. Proof of that. So I go slowly because, okay, don't want to be confused. Okay, what do I take? Maybe I move this up so we can see both things at the same moment. It's easier. So let's do this direction in part 1. So let's assume I have my G is in the subalgebra. I can express it this way with some polynomial H0. I will show H0 equals H, but at the moment this is not clear. Okay. With H0 being a polynomial in the Y variables. I use this abbreviation. Okay then. So now we look at what happens modulo the ideal J. Okay. So so remember. So what I route right now will be a congruence modulo J. So the H is congruent to G. Why? Because H, if you look here, H is the normal form of small g. Clearly, H and G are congruent modulo the ideal J. Okay, so I have this. But now comes the trick. You know what happens? Okay, now I use some intuitive notation. Okay. Okay, nothing changed. I just write the y's. Usually I don't write them. But now I say, okay, when I modulo J, yup. Let me think, do I want to do this? No, I don't want to do this. This is, sorry, this was rubbish because G is a polynomial in X. So what do I want to say is, okay, let me write it in what I think it needs explanation. I claim I can put here H0. And it's a congruence mod J. So why is that the case? So here. because, okay, I write it here. This is the whole trick. Okay, the h0 is a polynomial in the y's. You agree? But now what I do, I substitute the y's by the f's. Of course, this will give me a different polynomial, but modulo j, it's the same. Okay, because modulo j, since yi is congruent to fi mod j. So one should really think in this way. Okay. And this is the G. This thing is called that this I denoted G. Okay. So for understanding the proof, it's important that we think in terms of this congruence relation. This simplifies a lot. Okay. So then I have this, and okay, let me go on. Right, since now I use, since H is a normal form, no, just I should say is the normal form, it's much better, is the normal form, because it's unique of, it was defined, it's the normal form of G, of small g, modulo the ideal. Okay, what do we get? H0. Okay, here, maybe I'm H0 and H, they are congruent. Okay, so it must now be, if I make a reduction, if I reduce H0 to the normal form, mod, okay, with my Grabner basis, I must end up with the H. Okay, because H is the normal form. You see, H is the normal form. So any polynomial which is congruent to H modulo J must lead, when you do the division, must lead to the H. Okay. So good. Now, okay, this is important. Now from, so what do we get? Now from the H0 is a polynomial in the Y's. Okay. Okay, now I have a polynomial in the Y's. So now you should think again of my picture. I have the X variables and the Y variables. Okay, and these are the larger one. That's my elimination order. Now I have a polynomial H0. It only depends on these. And I reduce modulo my Grabner basis, but the Grabner basis is adapted to this elimination order. Then I know, and this was the contents of a previous lemma, I get that the result also depends only on the Y variables. This was a lemma, see a lemma. Unfortunately, I don't number my, on my notes, I number them by page number, but this is, do you remember this? I have a polynomial. It's this situation. I have a polynomial, this situation. I have a Grabner basis, okay, adapted to this. And then if I take a polynomial only depending on those, I reduce what I get, the remainder will also only depend on the Y's. Okay, that was trivial, by the way. So, okay, so what I see now, yeah, I'm done. I wanted to show H is a polynomial in the Y's. This is what I did. So the argument is a little bit, yeah, it's not so, it's a bit tricky. Okay. Okay, the other direction.
And do we also know already that H equals H0?
Right, we know that. We know that. Right, why do we, okay, good, thank you. I want to say, let's do it. H, note. So H minus H0. This is in J, okay? And right, what do I want to say? J. Let's see. I'm a bit confused actually. Let me see. I want to do.
We really need that h0 equals h in this
it. We
case.
don't need it. Let me check. Is this true at all? Yeah. Right. Okay. The point is, I think this is wrong. This is wrong. I just said, I think when I went through the proof, I claimed h0 is h, but it was wrong. We don't need it. Okay. And it's also not part of the statement. Sorry about that. Okay. Sorry about that. You got you okay, you catched it. So now the other direction. I assume h, that h be a polynomial in the y's. Okay. I want to show, what do I want to show? The G is in the subalgebra. So what do I do? Actually, I think I go backwards a little bit. Same idea as before. In H, which depends on the y's, I substitute the y's by the f's. And I get something that is congruent to H modulo my ideal J. Okay, it's the same trick as before. Okay, now if I look at this difference, G minus H up to F or. So this is then congruent to G minus H, and G minus H is congruent to 0 modulo the ideal. Okay. On the other hand, I know this. This is a polynomial only in the x variables. Okay, there is no y here. Now I use use J intersected with kx equals 0. I think we had this last time. Maybe I should say I gave okay, I proved it. I gave two proofs, one using Grabner basis and one, I think, geometric, and it's also very easy to see directly. So what we see in the end, if I combine this, I see that this must be 0. And I'm done. So I will ask Marco to have some exercise on this. Okay. So as I said, maybe I should say that because you don't know the theorem about the elementary symmetric polynomials, is that right? You didn't learn it? You don't know it? Somebody's nodding. Nodding means I don't know, okay? Oh, okay, good. So maybe famous example, okay? Famous example. Okay, but maybe I don't do it in full generality. I just do a very simple one, okay? Very simple. Symmetric polynomials. Let's do it just for two variables. I don't want to be complicated, okay? So, okay. I look at, how do I write it? Okay, I call a polynomial f. I have two variables, so x1 and f2. call it symmetric. Okay, if invariant under permutation or transposition or the under exchange. Okay, if I replace x1 by x2 and x2 by x1, it should be the same. Okay, this is symmetric. So let's have an example. Example, maybe x1 square plus x2 square is symmetric. You see, it's symmetric. Or, okay, but x1, so let's say this one is not symmetric. Okay. Now I look at the subalgebra of symmetric polynomials. Subalgebra. It's a subalgebra. I don't give you the name. That's very easy to see. The sum of symmetric polynomials is symmetric. The product is symmetric. So on. Now the question is generators. Now, I mean, now you could use the algorithm. I mean, if you have your Macaulay installed and so, you could just do it. Okay, one could you could compute it. Okay, but I tell you what is. I mean, I say you could compute it. What? I mean, it's not unique. I mean, is it correct what I'm saying? What could you compute? No, actually, no, I didn't give you an algorithm how to compute the system of generators. The only thing what I told you is how to find out. So, okay, sorry about that. It's confusing. If I give you a polynomial and you want to find out is symmetric or not, I mean, it's of course clear. You just exchange the permutations. Okay, so we don't need the algorithm for doing that. Sorry about that. But here is okay. Here is it known that these two polynomials, x1 plus x2 and x1 times x2 generate this subalgebra. Okay, so I think I'm not going to prove that without any preparation. Yeah, and more generally, these are examples of elementary symmetric polynomials. Yeah, called elementary symmetric polynomials. Okay. So if you haven't seen that, then you didn't learn about the solvability of equations by radicals in the lecture Algebra 1. No, didn't, because this plays an important role.
But we had it, but we just
we did learn that, but we did learn it. Wow, it was
last week.
No, it was actually Galois theory, and we didn't have much to do with symmetric polynomials. We had that in only one lemma where we have shown that one polynomial is unsolvable, and there we had it. Well, we scratched it maybe, but we really didn't go into detail.
Okay, so how is it for free polynomials? Let me say for, okay, similar. Okay, let's say call f. Now, if it depends on n variables, call this symmetric if invariant under permutation of variables. If invariant under permutation of variables. Okay, this is more general. And again, we can ask, what is the subalgebra of symmetric polynomials? And the fact is, this is the fundamental theorem of symmetric, okay, functions, so fundamental. theorem on symmetric polynomials. So it must be important, otherwise it wouldn't be called fundamental. Okay, so okay, the subalgebra of symmetric polynomials is generated by the elementary symmetric polynomials. And I have to define what it is in generality by the elementary metric polynomials. So what are those? So let's write them. Like sigma 1 is the sum. Sigma 2 is the sum of all products of different variables. Okay, you see it's symmetric. The sigma 3, you take now product of 3 variables which are different, etc. Okay, etc. Like the sigma n, there's only one option, it's the product of all variables. So these are the elementary symmetric polynomials. Yeah. Okay. And not only that, okay, moreover, they are algebraically independent. Okay, moreover, the sigma 1 up to sigma n are algebraically independent. Algebraic independent was over this again. What does this mean? I should say over K. Does anybody know what this means? Algebraically independent?
That the ideal of polynomial relations is 0?
Correct. Correct. But I write it explicitly. It means for all h in the y variables. Okay, if I substitute here and get 0, then the h must be the 0 polynomial. Means, okay, ideal. Now, okay, maybe I use this. We had this name, but okay, ideal of polynomial relations is 0. So I mean, now what we could do, we could, check it.
Short question.
Yes.
So that here the number is the same, is crucial, or is what we want, or is here
Which number?
Is y1 go until yn?
N is the same. N is the number of variables. This is
so
also
exactly
the number.
The same.
This must be the same.
Okay.
Must be the same, but it's hardly readable. Good. So, I mean, I say we have our algorithm, we could just test it, okay? So this we could check, but of course one can also prove it. I'm not going to prove it here. It was just the illustration. This is maybe the most important example that I'm aware of in algebra, okay? Here, in a way, it's not so interesting because you don't have any relations, just a trivial one, okay? So for instance, it's important in Galois theory, and it's important in, I don't know, almost everywhere is important. Okay. More questions? Okay. So I have more applications. So this was for subalgebras, but we can also compute intersection of ideals. So here's another application on intersection of ideals. Intersection of ideals. Okay. So why intersection? I mean, we can do all kinds of operations with polynomial ideas, and the intersection is the only one which is actually requires work. So let me maybe explain that. Let's assume I have two ideals and they are given by generators. One ideal I given by F1 up to Fs, let's say. J is given by G1 up to GT. That is the ideals in the polynomial ring. What's that? N variables, okay. Then, so what can we do? We can form the sum of ideals. We learn what is the sum. Computing the sum in the sense that I want to have a set of generators of the sum, this is trivial. I just take these generators, okay, and I list them together. So these are generators for the sum. So there is nothing to do here. We also had the concept of the product of the ideals, if you remember. Generators for the product, basically by definition, it's just this. You just take any, okay, Fi times Gj. So there is nothing to do. But how about intersection? Okay, that is not so clear. How can we find a system of generators of the intersection? Okay, now I'm going to tell you. And for the sake of completeness, it's always good to explain what is the geometric meaning behind, even though I'm aware without, algebraic geometry, this may be always a bit hard, but I do it as a remark because I think it's extremely helpful. So what is the geometric meaning? Geometric meaning. And as usual, if I say geometric, this is unreadable. If I mean geometric meaning, I now assume field algebraically closed. So I don't have any trouble. Then, okay, the following is true. We had the notion of the zero set. So one can show the zero set of the intersection is the same as the zero set of the product. Okay. The zero set of the product is the union of the zero sets. Okay, I think not every step here is clear. So what is easy?
We also had this as an exercise.
You had it an exercise. Very good. Very good. Okay. Very good. Then I don't have to explain it. So it's always good to have these examples. Let's say, right. Okay. What do I want to do? Okay. So if I have, say, I have the polynomial ring in two variables, just to have one example. Ideal generated by X intersected with the ideal generated by Y. This is the product, actually. It's this ideal. And it corresponds, just to have a picture. Okay, the zero set of the Y and the zero set of the X. It's a union of two lines. Okay, union of two lines. Okay, so the intersection of ideals corresponds geometrically to the union of the zero sets. Okay. Okay, so we had this example. Maybe I also want to say that in a way, you may think that, I mean, the intersection and the product, they give the same zero set. If you're only interested in the zero set, okay, why should I care about this intersection? I can just take the product. But I think in a way, the intersection is the better object. So maybe I can also make, we have this inclusion, this is always true. And in a way, let's say, okay. So this is maybe in quotes, better object. Okay, without, without, no, what do I mean exactly? But something that is, for instance, nice is, like if you have radicals ideals and you intersect, then we have a radical ideal. So in a way, somehow this thing contains the complete information about the ideals. If you just look at the zero sets, you don't see the complete information. Sometimes you lack some multiplicities and so on. Whatever. So this is motivation. So now I can describe the procedure to compute the intersection in the completely general situation with the following trick. Okay, theorem, let I and j be given as above by generators. Maybe I should, yeah, as above. Okay. Then, okay, then we make a very neat trick. Sometimes it's called, okay, embedding in the diagonal. So we consider the following idea. I call it delta. So I take one additional variable y, which I want to eliminate later. So I have one variable y, and I look at this ideal. I can write it this way, y times I plus 1 minus y times j. And I intersect this with kx. So meaning I eliminate the y variable. So I can write this, oh, sorry. I don't want to do it this way. Intersecting comes after. Let's, sorry, I was going too fast. I just want to, okay. This is the definition of the ideal delta. I can make it more concrete by writing the generators. So here I multiply all generators, and I think it was called S. The F's I multiply with Y, and the G's I multiply with 1 minus Y. I think this goes to T. Okay. Consider ideal in this polynomial ring. Okay, then, and the clue is this. The intersection of I and J I get as an elimination ideal. Namely, I just intersect my delta with Kx. Okay. So if you can compute elimination ideals, and I explained you in principle how to do it, the Grabner basis, we can compute intersection of ideals. And the proof of this is really simple, amazingly simple proof of this theorem. Okay, it's like two inclusions. So let's first take an F in I intersected with J. Right. Now I do a very silly trick. I write F, okay, this way is Y times F plus 1 minus Y times F. This is certainly true because the Y times F cancels. So this is an identity. This is true. You see? Okay, now, but then you see F, here is F. F is in I. So, yeah. So what I want to say, the YF is here and the 1 minus YF is here. So I'm in delta. You could also express it in terms of the generators. Okay. So, okay. So I've seen I've proven this inclusion. Okay. And the other direction. Okay. Now let's assume I have an f on the right-hand side. It's in delta and kx. Say, because if it's in f, I can write it as a linear combination of the generator. So I could write f in some way, it's y times sum over I, ai. This is a coefficient polynomial, it depends on x and y. Okay. X and y, fi plus 1 minus y, sum, let's say, over j, bj also depends on x and y, derived gj. Okay, with coefficient polynomials. Now I just make substitution. If I substitute y by 1, I get yields. Okay, if I substitute y by 1, the f doesn't depend on the y, so f is unchanged. And what I get is here the y becomes 1, then I have this sum ai x1 the fi's, and this whole thing disappears. Okay, because the y becomes 1, then this becomes 0, so this disappears. Same if I, okay, analogously, if I substitute y by 0, this is a 0. It's the same trick. Then I get the sum over the j's. So now the first thing, I mean, this vanishes. And I get here bjx0 tj. So what I see, so here I see this is in I and here is in j. So I've proved f is in I intersected with j. And I'm done. Very short proof. It's a nice trick, okay? Right. I mean, this also works if you have more than 2 ideals. If you have many ideals, maybe we have an exercise on that. It also works for many ideals. Okay. Okay, a possible application. So actually, I'm not 100% convinced of this application, but it's in principle possible. How could we compute GCD of multivariate polynomials? GCD of multivariate polynomials. Okay. How? Okay. I ask you, if I give you 2 polynomials in one variable, how would you compute the GCD? Do you know that? Größter gemeinsamer Teiler.
Maybe check the decomposition in irreducible polynomials.
Okay, this is right. This is possible, but it's not an efficient method. The same
No.
is, yeah, same with numbers. GCD of 2 integers. I mean, if
The
you can
Euclidean algorithm.
Euclidean algorithm, this is the right answer. I mean, because this is efficient. Okay. Actually, for polynomials, it's not that bad. One can factor polynomials efficiently, but this is not trivial. For numbers, it's not known. Okay. Okay. For univariate, comment. For univariate points, use Euclidean algorithm. Okay. But now, if you have several variables, what can we do? Now I'm going to explain you that in principle, we have a method. Okay, and how is that? By intersection of ideals. So let's assume I have two polynomials, f and g, in n variables. Okay, first thing is the GCD. Okay, I can express in terms, okay, what do I say? The GCD, okay, I do it this, sorry. Instead of computing the GCD, I will compute the least common multiple. So this is a general fact. GCD my least common multiple is the product. Okay, so instead of computing GCD, we can as well compute this least common multiple. Okay, so now this is just the observation. I look at the principal ideals generated by F, generated by G. Two principal ideals I intersect. Okay, so then we know, yeah, because the polynomial ring has unique factorization and so we know this is generated by the least common multiple. Okay. So if you trust the algorithm before for computing intersection of ideals, it will give you this. You can compute it. Principle. Okay.
You use now the argument about the unique factorization for multivariate polynomials.
This is true. You know that. This is very, very important. This is due to Gauss. So he proved that polynomial rings over fields in many variables are unique factorization domains. And I'm sure you had this in Algebra 1.
We had it just for one variable.
Only?
Yeah, we
Really?
certainly didn't have it for many variables.
Really? So this was Dirk Cousin. Okay. Okay, now I understand why he could do Galois theory. When I do it, usually I don't manage because I give more other.
No, he did it differently. He did it differently without much consideration of polynomials directly. We did it really over the algebraic way.
What?
Like
what did you do? What did you do? Galois theory or what? Or
we did Galois theory.
That's okay. But I'm just saying, if you don't discuss certain more basic things, then you have more time for Galois theory. Okay. Okay. But this is very important. Okay. It's called Gauss lemma. Shall I write it? Okay. Recall. I say recall.
It was just that it is a factorial ring, right?
Yes.
Right. Okay, we
good.
had it. Of course.
Good.
We had
Everything good.
but we just said for one variable.
Only for one.
But only for one. Yeah.
Only for one.
That's true. Only for one. Yes.
Okay.
Not with general Gauss lemma. Yeah. That is
I
true.
say that. Because this is, I mean that, as you may have noticed, the polynomial rings over fields are the most important example of what I'm going to tell you. And this is tricky. So this is factorial. And this is due to Gauss. But I don't have time to explain it now. I mean, maybe I tell Marco, maybe he can explain a little bit in the exercise about this, because this is fundamental. It's very important.
Would we prove be similar like for the one?
Yeah. Okay, you rely. Okay, what you do is this.
I mean, like generalization.
Okay, the idea is this. Okay. Okay, I should say the theorem is this. Gauss. Okay, maybe I should write Gauss. Well, Gauss said, if A factorial ring, then A, now we join any variable, is factorial. That's what Gauss proved. So, and if you apply this principle several times, then you get it. Okay. So K.
Yeah. Okay.
Okay. But this requires
Yes, of course.
this requires some work. And the idea is, okay, idea. Let's say capital K is, okay, field of fractions.
No, the one step we had, that crucial step we had, of course.
Sorry, this implication you had.
Of course. That's exactly what we told you. I told it to you.
Okay, then I don't have
but
to.
in one variable we had it, of course.
Okay, in one variable, but over, not just over fields, but over rings.
Over rings.
Okay,
We had
good.
it in one variable.
But then the application, but okay, then you had it.
Okay.
Good. Everything good.
This was simple.
Okay. Yeah. Okay. Good. Sometimes one knows things. Yeah. What do I want to say? Yeah. Okay. So last application. Oh, I have 10 more minutes. Maybe I don't know whether I managed. The last application. Let me do it. Quotient of ideals. Okay. The purpose is just to show one can do all these calculations with the grammar basis. So what is the quotient? We had it, I think, but maybe recall the definition. Let I and j be ideals in our polynomial ring, as usual. Okay, the ideal quotient okay, is I divided by j. I had it in chapter 1, but it was so abstract that maybe don't know whether you remember. So set of f with the property that if for all g in j, if I take any g in j, multiply with f, then I end up in I. Okay, so no, it's a bit abstract. What is clear? I mean, it's easy to see this is in fact an ideal. You check it. It's an ideal and it contains I. So when you divide, you get something larger. Okay, by definition, it's clear. Okay, I can't write geometric meaning. You know, what is the geometric meaning? Maybe I tell you next time. Let's rather do this little, let's call it proposition. Okay, it's a little thing. No, there are two things that I want to say. Okay, first thing is observation. So let's say I want to divide I by the ideal generated by G1 up to GS. Okay, then this is a trivial observation. You check it for yourself. This will be an intersection of these ideals. Can we put parentheses? It's easy. You check it yourself. So the point is, right. So we have here, if I want to compute quotients, it's reduced to computing the intersection. And I also need to know how to compute quotients by principal ideals. Okay, I have here intersection. Sorry. So I have here intersection of ideals, which I discussed before. Now let's discuss quotient by principal ideals. This is in the following simple proposition. Let I be an ideal in the polynomial ring. And then I have G, another polynomial. Maybe I don't want to write these variables all the time. It's a mess here. Then I have another polynomial, but it's many variables. And okay, I do it this way. I say I intersected G, principal ideal, has these generators H1 up to HR, or okay. I know, in principle, I know how to compute intersections. So I intersect my ideal I with the principal ideal generated by J. I get the list of generators H. So then I say, okay, now I can compute the list of generators for this quotient ideal. It's just this. You see, H1 divided by G makes sense. It will be a polynomial, okay? Because all these, I mean, all these H here, they are multiples of G. So these are polynomials, and I just write this list of polynomials. Okay. So the point of this proposition is if you can do intersection of ideals, you can do quotients by principal ideals. Okay, and I have 3 more minutes, and this is just enough to give the proof, which is extremely simple. So first I note HI divided by G is in I divided by G, because when I take HI divided G, I multiply with G, I get HI, and this is in the ideal I. Okay, so this is clear. This is one. So this gives one inclusion, and the other inclusion is this. Let's say I have an F in the ideal quotient. Okay, then when I multiply F with G, by definition, okay, by definition of the ideal quotient, I'm in I. But I'm also in the principal ideal because this is a multiple of G. So say, okay, now I express my FG as a linear combination of generators. Let's say sum I, HI, AI, HI. Okay, now I use, okay, this, the H generate. Okay, but then I just divide, it's enough. Now I divide by G. Okay, and I know this division is okay. I stay in the polynomial ring and I'm done. I have written F as a linear combination of the HI divided by G. Okay, very simple lemma. Right, so what right. Okay, maybe next time before I start with a new chapter, I will tell you what this means, quotient of ideals. Okay, in terms of 0 sets. And then we will start, then this will be the end of this very concrete chapter about Gröbner basis. Then the plan is to go back to the abstract theory. So I will continue with Attia McDonald chapter 2 and discuss modules. So this will be quite a long chapter. At the beginning, it will be, you know, just concepts. And then I don't think it will be very difficult at the beginning. Okay. But it was important for me to show you that, I mean, what we discussed in chapter 1, ideals in rings. If you take polynomial rings and you have the concept of Gröbner basis, you can actually compute with these objects. It's very concrete. Okay, it's not just abstract blah blah. I mean, you can compute with them, right? And by the way, I mean, in the next chapter, I will talk about modules. You can also compute with modules concretely. Also for modules, you have a notion of Gröbner basis. Okay, but I decided I will not enter this. It will just take too much time. But everything, yeah, also what I will tell you about the modules can also be computed in. Okay. Questions or comments or?
Yes.
Mhm.
I have some questions.
Yes.
First question, I didn't really understand earlier when we said that H needn't to be H0 in this proof.
Yes.
Then I didn't really understand how we then could conclude that.
Okay, let me go.
Yes.
Yeah. Let me go to the proof. So first the statement, so that we remember. I think it was, you are referring to this, okay?
Yes.
Okay. So what we go, let's do this. I think we first did this direction. If it this direction, we should look at, I think, right? So I have a polynomial h. I make division with remainder. I get, sorry, I have a polynomial g. I take the remainder, which I call h. And the claim is if my g actually lies, excuse me, if the g was in the subalgebra, then this normal form should only depend on the y variables. Okay. Okay, let's go back. So maybe can you tell me exactly which step is unclear to prove?
Yes. So we took some h0.
Yes. So we started here with this.
And we need to show. I thought for this moreover statement in the proposition.
Where is the moreover statement?
It's that
Aha,
moreover than
I
G
didn't.
is.
Oh, it's right. I didn't prove this. Huh?
But it follows from the backwards direction. I think there we got that G minus H of F1 to FR is 0. So this is exactly the statement, right?
That's right.
Okay.
This is correct.
Yeah, okay.
So this is correct. That's right. So yes, this is correct.
Yeah. So we just need to prove it in just one case because it's equivalent.
Yes. Yeah.
Yeah. Okay. Okay.
Problem solved.
Yes.
Anything else?
Yeah, I would have a short question towards the last lecture if we have time.
That's okay. I mean, we are 4. It's
Yes.
almost, it's extremely private. This is okay. So it's the 21s. But I see that some people are also looking at the videos, or is that you?
Could be that it's us, I don't know.
So the last one was the 25th May, I think. Okay, so this one. Okay.
Yes. So if you go to page 4.
Page 4.
Yes. It's just to be sure. There we had this theorem that we can just choose the polynomials that only depend on the first, on the last variables in order to get the values. And then we went to the proof, and isn't it actually sufficient to have this statement in the star? You know where there's a star?
Okay, I don't precisely understand the question, but a question in principle, everything is recorded. I mean, should we do that? Maybe we should stop the recording before.
Okay.
That's because this is